Hi, welcome back. So in previous videos, we've shown that if a function f is continuous and if a path gamma is bounded variation, then the Riemann-Stieltjes integral of f d gamma is defined. Now, that's really good to know, except that we don't have any criteria for proving that a path gamma actually has bounded variation. So that's a bit of a problem. We've actually shown in the previous video a counterexample that illustrates that even if gamma is differentiable, it still might not have bounded variation. And so this brings us to our next theorem, which is basically guaranteeing that gamma has bounded variation, but we require a slightly stronger condition than differentiability. We require that gamma is continuously differentiable. So this theorem, first of all, says that we get bounded variation from that condition, right? If gamma goes from A, B to C, with gamma prime, it exists and it's continuous, then gamma has bounded variation. But furthermore, we go on and state that the variation of gamma is actually equal to this integral of the modulus of gamma prime of t from AB. Now, I want to remind you that this is a normal integral. This is a real integral because this is a real valued function and this is dt, but it may be regarded as a Riemann-Stieltjes integral if we think of dt as recording the path gamma. If we think of dt as recording the path, which is the identity map from AB to AB, and this then becomes the function f. So this is somewhat confusing. The function f here is this. From the point of view of Riemann-Stieltjes integration, this is the function f in the integral, and the path is the identity path from AB to AB. So with that kind of attitude, this can be regarded as a Riemann-Stieltjes integral. And it's important because we need to know whether our theorems apply to it. So now, in case this doesn't look natural to you, in case this looks like some crazy made up thing, I want to remind you that if gamma goes from an interval AB into the complex plane, then, so this would be maybe gamma of A, and this might be gamma of B. So if we have a path from AB to the complex plane, then the derivative records the velocity vector, and the modulus of the derivative records the speed, the length of the velocity vector. Now, if you integrate the speed, what you're really doing is you're integrating the rate of travel, and that makes sense that that would calculate the total distance traveled, which would then be a length. So it is a familiar principle from physics that if we integrate something like a speed, then we get a total distance traveled, not a total displacement, but a total length along the path. So that formula is supposed to make a bit of sense there. Now, let's get to proving it. Now, the first question is, well, before we prove it, I want to remind you of a previous theorem. You should maybe review a theorem about uniform approximation of derivatives by difference quotients. When we were dealing with this function q of wz, we proved that the difference quotient function for a function f of w minus f of z over w minus c, that function can be uniformly approximated by the derivative in this sense. For every epsilon, there exists a delta such that for every z in some compact set on which f is defined, and for every w and z delta close to z naught, and also in that same complex set, then this, that same compact set, then this difference between the difference quotient and the derivative can be made uniformly less than epsilon. So we will use that in the proof, so I want to remind you of it. So the first question here, so what we're going to do is we're going to calculate this integral carefully, and we're going to prove that it's equal to the variation. The first question is this integral even defined? So we're going to start with this. So note this integral, sorry, that's not an f, that's a gamma prime. This thing has continuous integrand. The integrand here is not, so there's no function f, right? The integrand is this thing, which is playing the role of f. And it has bounded variation path. And the path is really the identity path from AB to AB, which has variation b minus a. So, so for those reasons, this integral is defined. So this integral is defined. And when I say that it's defined, what I mean is that the limit in the definition of the integral converges. So this integral is defined. It equals something. That doesn't show that it's equal to the variation. So what we're going to do next is we're going to show that it's equal to the variation. But merely on the basis of the fact that this integral is defined, then we can say that we can choose a partition which approximates it rather well. So what we're going to do is we're going to let epsilon be greater than 0, and we're going to try to show that there's not much difference between the variation of gamma with respect to p and this integral. So we're going to let epsilon be greater than 0, and we're going to choose delta 1 so that if the norm of a partition p is less than delta 1, then we get the integral estimate via p, by means of p, is going to be very close to this integral. So then the integral estimate, which would be the integral from 1 to m of this thing, so gamma prime of t, tau I, gamma prime of tau I, and then modulus of that, and then times, so that'll be ti minus 1. So this thing is going to be, minus the actual integral dt. That difference will be small. And I want it actually less than epsilon over 2. So what I'm doing here is I'm saying, look, if the integral is defined, then its integral estimates will get closer and closer to it as the partition norm approaches 0. And so I can invoke the definition of that partition norm limit. And I can say if the partition norm is already small enough, if it's less than delta 1, then the integral estimate will be very close to the integral itself. And I know that everything here exists because I've invoked that previous theorem. Now, is this the right integral estimate? The normal integral estimate, if you'll recall, it says the integral of f of tau I gamma of ti minus gamma of ti minus 1. So you might worry that I've forgotten my gammas here or that I've forgotten my f. But you see, this applies to the estimate for the integral of f d gamma. And our function f in this case is actually the integrand, which is this function. So that's why I've plugged in the tau I to the function modulus gamma prime. And then our gamma here is actually the identity path because it's dt. And so this gives it, that's why I haven't written any gamma here. So this thing is very close to this integral then. Now, I also want it close. So I've got it epsilon over 2 close to the integral itself. I'm going to want it also epsilon over 2 close to the variation estimate by means of the path gamma. So the next thing I'm going to write down is I'm going to compare this same integral estimate here to the variation estimate or the variation with respect to gamma. So let's say consider, and then we're going to calculate in a detailed way. We're going to compare this same thing to the integral estimate v gamma, so to the variation estimate v gamma p. So what is the variation estimate? That is the summation I equals 1 to m of, now we have modulus gamma ti minus gamma ti minus 1. Okay, so that's the variation estimate by means, so that's v gamma subject to p. And then I'm going to subtract from this just this exact term, the summation gamma prime of tau I ti minus ti minus 1. And then I get modulus around that summation I equals 1 to m. So basically, I'm going to consider this thing. So this, I wish there were. In fact, I can use color to do it. We've got a lot of modulus signs here. And I want to point out that I have a modulus sign along the outside, which basically means I'm taking the modulus of the difference. But I also have modulus signs along the inside because I'm reasoning about the moduli of these various things. So this is the thing that I also want less than epsilon over 2. I want to control this less than epsilon over 2 so that I'll know that the integral estimate is close to the integral and the integral estimate is also close to the variation estimate. So we need to compute this thing. It's going to be a little bit of work. The reason it's a little bit of work, I should have pointed it out before. This is actually the very first integral that we've exactly calculated in this course. We've proven that integrals exist, but we haven't actually completely calculated their values. And so that's one of the reasons why this proof is going to be hard. So let's try to control this. So what I'm going to do is I'm going to factor a ti minus 1. Well, first, I guess I'm going to merge the sums. And then I'm going to factor a ti minus 1 out of this. So let's first just merge the sums, which will be easy. So we get the summation on I of the modulus of gamma ti minus gamma ti minus 1 minus modulus gamma prime tau I times ti minus 1. All of these terms can be interpreted fairly naturally in terms of distance and speed. So this is the displacement in step I along the way. This is the time in step I, and this is the speed. So basically what we're saying is compare the time, a little bit of a short time duration times your speed to the total displacement in that little step. And they should be close, right? Well, in theory, they should. So let's keep working here. So now this is the sum of everything here is inside the summation sign. And now I'm going to factor a ti minus 1 out of everything. This thing doesn't have a ti minus 1, so I'm going to have to divide by it in order to factor it out. So let's do that next. So we've got these outer modulus signs, and then we've got the summation I equals 1 to m of gamma ti minus gamma ti minus 1 modulus over ti minus 1. And that's minus, and now I'm going to factor out of gamma prime of tau I modulus, and then everything is going to multiply ti minus 1. So it's not at all clear. It might not be at all clear why I want to do that, right? But I want to factor the ti minus 1 out of that product. There isn't one here, so I'll put it here. Now, the reason I want to do this is because I want to start thinking about this. Notice the similarity here between this and this. So now, however, we've got a bit of a problem with these absolute value signs, right? Notice these absolute value signs here and these absolute value signs here, and we've got a difference of absolute value signs. And so what I want to do is I want to kind of merge those. Now, notice here that ti is always going to be greater than ti minus 1. And if so, then I can absorb that inside this absolute value signs. In other words, it's harmless to accidentally take the absolute value or modulus of this thing because it's a positive real number. So I can absorb that there. And now this is just a modulus of something, modulus minus the modulus of another thing. And that obeys a triangle inequality. So the triangle inequality actually goes the direction that we want. This difference, the difference between these moduli is less than or equal to the modulus of the difference. And so I'm going to replace this with the modulus of the difference. It's kind of the other triangle inequality, if you will. So I'm going to have the modulus of the difference here, gamma ti minus gamma ti minus 1 over ti minus 1 minus gamma prime of tau I, and I'll put the whole thing in absolute value signs. Now, so that deals with this term and gives us a less than or equal to between what's here and what's here. Now, does that less than or equal to apply to everything? When we multiply it by this non-negative number, then that still is sound. So that's the right inequality because this number is non-negative. And then here, I'm just summing it up. So I can continue. I can just, if it applies to each term, then we get the sum. And then again, we still have these huge absolute value signs around the entirety, but they start to matter less and less because now that I've done this, this term here is definitely non-negative, and this term is definitely non-negative, and every term here is definitely a non-negative real number, and so these outer absolute value signs don't actually matter. Okay, so now what? Now this is starting to look very much like this, right? We've got a function, gamma, evaluated at 2 points. We know that those points are pretty close to each other, right? because if the norm of the partition P is less than delta 1, then we get a little, or is less than some other delta maybe, then we get some control over the distance between Ti minus 1. And because the tau i's are between the Ti's, we also get control over the distance between the tau I and the Ti's, and the Ti minus 1 as well. So we get control over these things being close to each other. And this looks like this term. And so we can control this term to be less than, well, whatever we need. So what do we need it to be less than? We want this ultimately to be, we want the whole thing to be less than epsilon over 2. And so it would be nice if this term were less than epsilon over 2. Then we could factor out an epsilon over 2, and this summation would end up giving us a b minus a. And so what we're going to do here is we're going to control this thing so that it will be less than epsilon over twice b minus a. So that's the plan. So by the uniform approximation of the derivative theorem, in other words, by this theorem right here. So choose, I'm going to choose a delta 2 for epsilon over 2b minus a. In other words, choose a delta 2 so that if z comes from the compact domain of this function, and if w and z come from the delta ball of that z intersected with that compact domain, then this will be less than epsilon over 2b minus a. And then, so if the partition norm is less than that delta 2, then what will happen? Well, the taus will be between the Ti's. The Ti's will be no farther apart than this. The taus will be, their distance from tau will be no more than this. And so all of this stuff here actually will apply to the taus and the Ti's. And so this thing will indeed be controlled to be less than epsilon over 2b minus a. So that's going to give us less than or equal to summation I equals 1 to m, and then epsilon over 2b minus a, and then Ti minus 1. And now everything else is easy. We factor this out. That's summation, well, I should factor it out. That's epsilon over 2b minus a times the summation I equals 1 to m of Ti minus 1. But this is just a telescoping summation. All these Ti's will cancel except the first and the last. So that's just Tm minus T0 ultimately, which is just b minus a. So that's epsilon over 2b minus a times b minus a, which of course is epsilon over 2 by design. So that tells us, what do we learn? We've got control over the distance between the variational estimate, sorry, got myself lost here, between the estimate of the variation v gamma p and the integral estimate by means of the partition P. The distance between those two things is less than, are any of these strict? It's less than or equal to epsilon over 2. I probably have a strict one here. Where is it? It's here. This one is strict. So that's less than epsilon over 2. And we also have that the same thing can be controlled so that its distance from the integral is less than epsilon over 2. So so what do we conclude from this? For P, whose norm is less than the min of the delta 1 and the delta 2 that I chose, then the variation of gamma with respect to P is very close to this integral, which I know exists, with a distance no more than epsilon, less than epsilon. And what does that show? That shows that this function has a limit which is equal to this integral. So the limit of the variation function as a function of P, as partition norm goes to 0, this thing is equal to the integral of the modulus of gamma prime dt, that's from a to b. And if the limit is equal to that, then it follows that the supremum is equal to that, because we proved that, well, that happens whenever we have an increasing function of the partition. and this is an increasing function here. So the supremum is also equal to the integral from a to b of gamma prime of t dt. So what's this supremum? That supremum is just v gamma by definition. And so that tells us that v gamma is going to be equal to the integral from a to b of gamma prime of t dt. So why was this hard? This was hard because this was the first time we actually calculated an integral exactly in this course. In order to do it, we needed to use this uniform approximation of the derivative. There is a bit of fundamental theorem of calculus going on here. Notice that we've got the integral of a derivative here. This is certainly related to the fundamental theorem of calculus. And we'll say the same proof strategy when we use this very same theorem to prove the fundamental theorem of calculus shortly.